So following on from the previous video, we got to this stage here. We got to this stage here where the area of the parallelogram is given by this, and well, we would then rotate this 90 degrees, and then this would be 90 degrees. So this is 90 degrees, and then this would be 90 degrees. So when you rotate this 90 degrees, whenever you have the magnitude of one vector and the magnitude of another vector, and you cosine the angle that exists between the two, whenever you have this kind of a relationship, then you can jump to the dot product. So we've seen this many times. So by now I'm asking you to be able to accept that you can jump from here to here. So you trying to do the whole thing here is the same as you taking the dot product of this vector, which is a prime, and then the dot product of this vector. So we got to this stage here. So now it's just a matter of finding out this vector. So whenever you have a vector A, let's say this vector A here is given by A1 across, so A1 across, and then A2 up, A2 up. So that would be this. If you rotate it 90 degrees anti-clockwise, this point here will then move to here. So if you look at this horizontal line, if you rotate it 90 degrees, then that horizontal line will become this line here. So this is A1 up, this is A1 up, and then A2. So this line here will then become this line here if you rotate it 90 degrees anti-clockwise. So this will be A2, this line here will be A2. So whenever you know the vector A, you can actually get vector A prime. So vector A prime, vector A prime will be you moving A2 in the negative direction. So you moving A2 in the negative direction, and then it will be you moving A1. A1, which is this length here, A1 in the positive direction. So that would be A1. So if you have vector A, if you rotate it 90 degrees, you can obtain the vector A prime, which will be given by this. Okay, so if you want to work out the area of the parallelogram, it would be you performing the dot product on A prime on this vector here and this vector here. Okay, so let me illustrate this from here to here. So from here to here, if you have vector A here given by A1 across, A2 up, rotate it 90 degrees, that will then take you to here. So this length here will be this. This length here will be this. So your new vector A prime is given by you moving in the negative direction, A2. So that would be this, and then you've got to move in the positive direction, A1. So A prime would be given by this vector. So if you want to perform this operation here, A prime dot B, so that's A prime here, dotted with this vector here. So it will be you getting this vector and then dotting it with this vector. So you would then get this times this, which will be this, and then this plus this times this. That would then be this. Tidy this up because this is a scalar. It's just a number. So this will be a number. This will be a number. So you can't switch them around. Well, this whole thing here will be a number. It won't be a vector. It will be a number. So the area of the parallelogram is given by this. Okay. So rather than if you have one vector and another vector, to work out the area of the parallelogram, you would need to rotate this 90 degrees to obtain somehow obtain A1. But that's an easier way. So normally we would need to do all this to get to here. Because we know we are going to need to do this process many times, we are going to give it a special name. We are going to use well, we're going to call it a special name, the determinant of hang on, this should be a, bear with me, this should be just a here. So rather than you performing rather than you rotating this 90 degrees each time and then extracting a prime, you can't just do this. You can't just do this. You can't just do what's called the determinant of A and B. So because we know we're going to perform this many times, we just assign it a special name, the determinant of one vector and another vector. So for you to work out the area of the parallelogram, rather than rotating it and extracting this vector here, you can just do this. Let's just call this A1 and this A2. So this vector here is A1, A2. So this vector here will be this, and then the vector B here, let's just call it B1 across and then B2 up, B1 across. So this vector here is given by this. So now for you to work out the area of the parallelogram, rather than rotating it 90 degrees and then blah blah blah, you can just do this. It would be this times this. That will then give you this, and then take away this times this, and then this is exactly the same as this. So our old method would be us. Our old method would be us rotating this 90 degrees and then somehow extract a prime just in order to work out the area of the parallelogram. Well, the new method, because we know we need to perform this many times, we assign it a new name, the determinant of one vector and another vector. So now this is your vector here, this is your A vector, and then this is your B vector here, your B vector. So now just do this now. This times this, which will then give you this, and then take away this times this. So this is exactly the same as this. So in general, if you want to work out the determinant of one vector and another vector, so write this as this vector here, and then this vector as this. So now it's simply this times this, take away this times this, and you don't understand at this moment. You don't understand why we need to do this. I will extend it to 3D in the next video, but at the moment I'm just asking you to accept it for the time being. Okay.